All right, question 31 on the math subject GRE practice test. We get some probability here. So let's see, 4 cubes, each with faces numbered 1 to 6, are to be rolled. So dice. When each cube is rolled, each number is equally likely to appear on its top face. Yeah, you think? What is the probability that at least 2 of the cubes? This at least phrase here will be really important. It's a big red flag for you. At least 2 of the cubes will have the same number appear on their top faces. Okay, so if there's one trick to remember with probability questions like this, is that it's often very helpful to consider the complement. When you see this phrase, at least, there's your big red flag, now it's red, that maybe you shouldn't calculate this probability directly, because if you think about what at least 2 of the cubes having the same number appear on the top means, that's really 3 different cases, right? That means exactly 2 of the cubes or dice will have the same number, or exactly 3 have the same number, or all 4 have the same number. Can you calculate the probability of each of these different cases and then sum those probabilities to get your answer? Absolutely you can. In fact, just for practice, I'm going to do that towards the end of the video. But you know what's a hell of a lot easier than calculating these 3 probabilities? Calculate 1 probability. The complement of at least 2 of the cubes having the same number is that all 4 cubes have different numbers. If I can calculate this probability, all I have to do is subtract this probability from 1, and that will give me my answer. One more little tip that helps me anyways when I'm dealing with problems like this, and this might seem kind of silly, but whatever, it helps me, is to think of the different dice as having different colors, right? There's a red one, a blue one, maybe a green one, and a purple one. Sure. I'll even take the time to make them 3-dimensional for you. Beautiful, huh? Maybe it's just me, but if they all look the same, it's easy to kind of double count cases or forget to count certain cases. Anyways, what's the probability that all 4 have different numbers? Well, generally when you're trying to figure out probabilities, the probability of any event is the cardinality of the event space divided by the cardinality of the sample space, which sounds a lot harder than it is. It's just saying, count how many ways this thing can happen and divide that by like how many different things could happen. Maybe we start with the cardinality of the sample space. How many different things could happen? Well, there's 6 options for what the red die could end up being. There's 6 options for what the blue die could end up being. Look at that, color coordination. 6 for the green and 6 for the purple. So in total, I have 6 to the 4th power, whatever number that's equal to, as the cardinality of my sample space. Note that if your dice weren't colored, you might think of 3 1s and a 2 as an outcome, instead of realizing that there's 4 different outcomes where you get 3 1s and a 2, because the 2 can be purple, green, blue, or red. Anyways, what about the cardinality of the event space? How many different ways can I roll these 4 different dice and end up with different numbers up top? Well, think about rolling the red one first. It can be whatever the hell you want. There's 6 options for the red one because it's the first one that you've rolled, so it can't possibly pair up with anything else. Then think about rolling the blue one. How many options do you have for the number that could appear up top? Well, there's 5 different options. Why 5? Because it can be anything other than the number that appeared on the top of the red one. What about the green one? Similar logic tells you there's 4 options. It can be anything other than the one that appeared on the blue or the one that appeared on the red. Note that by construction, those are different numbers on the red and the blue dice. Finally, the purple one, there's only 3 options because 3 of the 6 numbers are already used up on the red, blue, and green dice respectively. The number of different ways that you can roll these dice and end up with different numbers on top is whatever 6 times 5 times 4 times 3 is. And the probability of this event, the probability that we end up with 4 different numbers on top, is whatever this divided by this is. Let's see, I can cancel out the 6's. I can take 2 from the green 4 and the purple 3 and cancel that with this 6. So that would leave me with what, 10 over 36, I guess? Right, this 5 times the 2 that's left here, and this 6 times this 6. Then I can reduce that one more time, because these are both even numbers, and get 5 over 18. Don't bother looking for the answer of 518, because 518 is the probability that we get 4 different numbers. That's the complement of the probability that we want. We need 1 minus 5/18 to get our answer. 1 minus 5/18 is 13/18. 13/18 looks like it's answer B. Contrast that with trying to solve the problem a little bit more directly without considering the complement. We still have the same sample space, so the cardinality of the sample space is the same. To figure out the cardinality of the event space, we have to sum these 3 different cases. So I don't know, the cardinality of event 1 maybe would be the number of ways we can have exactly 2 of these dice show up with the same number up top. How many ways can we do that? Well, we first have to choose which of these dice end up with the same numbers, right? Is it the red and the blue that are the same, or is it the red and the purple are the same, or the purple and the green, or what? We have 4 dice. We have to choose 2 of them to match up. Once we choose which 2 match up, we have 6 choices for what number appears on the top of those 2 dice. Right, so maybe from here I've decided that the red and green dice are going to match up, and from here I decided they're both going to be the number 4. Sure. I still have to figure out the value on top of the other 2 dice purple and blue in this example. How many options do you have for the purple die? Well, you'd have 5 because it has to be different than the number on top of this one. Finally, we have 4 choices for the number that appears on the top of the last die. I don't even remember what color it is at this point. The total number of ways that we can have exactly 2 of the dice have the same number is whatever this product is equal to. In case you're unfamiliar with this notation, it's sometimes written NCR. It's the number of combinations of size R from a group of n. And it's just equal to n factorial divided by r factorial times n minus r factorial. So in the case of 4, choose 2. N would be 4, R would be 2. We'd have 4 factorial over 2 factorial, 2 factorial. I can kind of cancel from this 4 factorial and this 2 factorial to leave me with 4 times 3 up top. And then I still have this 2 factorial, in other words, 2 down on the bottom. This 4 and this 2 reduce, and I'm left with 6. 4 choose 2 is equal to 6. So this product is 6 times 5 times 4. What about case 2? The cardinality of event space 2, maybe? The number of ways we could have exactly 3 of these dice have the same number up top? Well, first we have to decide which 3 dice have the same number. So from these 4, we have to choose 3 of them. Once we decide which 3 are going to have the same number, we got 6 options for what that number is that appears on the top of those 3 dice. And we have 5 options for what appears on the top of the other die. 4 choose 3, as you can verify by going through the formula, is just equal to 4. Oh yeah, that makes sense. The number of ways I could choose 3 of these 4 dice is exactly 4. Wait, why does that make sense? Because when you choose 3 of the 4, you're essentially not choosing 1 of the 4. So there's 4 different dice that you can choose to be the one that doesn't match. Oh yeah, that makes sense. Anyways, the cardinality of the second event space is 4 times 6 times 5, whatever that product's equal to. And the cardinality of the third event space, well, we have to choose all 4 of the 4 dice. If you want, you could say 4 choose 4, just so the formulas look more similar. But 4 choose 4 is just equal to 1. There's only one way you can choose all 4 of these 4 dice. And then you got 6 options for the number that appears on top of those 4 dice. We know the cardinality of the event space for each of these 3 different cases. So the cardinality of the total event space is their sum, 6 times 5 times 4, plus 6 times 5 times 4. Right, just rewriting this in a different order, plus 6. Because again, 4 choose 4 is just equal to 1. I want to divide that by the cardinality of the sample space, which is 6 to the 4th power. I don't have a calculator, so maybe I can reduce this a little bit in my head. I could factor a 6 from each of these terms and cancel it with one of these 6's. Then I'd have 6 times 5 times 4 plus 5 times 4 plus 1 divided by 6 to the 3rd power. See, I have 6 of these 5 times 4 things plus 1 more of these 5 times 4 things. So I got 7 of these 5 times 4 things. 5 times 4 is 20. 7 times 20 gives me 140. Plus this one, I got 141 divided by 6 to the 3rd power, whatever the hell that's equal to. But I just realized there's a 4th case that I didn't include in this list. We could end up with 2 pair of matching dice. Figuring out the number of ways you can have 2 pair of matching dice is actually pretty tricky. I know because I just did it and I got it wrong. So I paused the video, figured it out, deleted, and you're watching the second cut. Guess I didn't need to tell you that, but whatever. The number of ways you can have 2 pair of matching dice, well, you might think of it as I did, as from the 4 dice we have to choose 2 of them. That'll be kind of my first pair. There's 6 different numbers that can be up top that first pair. That leaves me with 2 dice. I have to choose both of them to make my second pair. And then there's 5 numbers that can be atop that pair. The problem is this double counts stuff. That's the mistake I made the first time through, right? Think about in this step, maybe we chose the red and the green die. This is saying there's 6 numbers that could be on the top of the red and green die. So I don't know, maybe they're both 4s. I then choose the remaining 2 die, blue and purple in this case, and there's 5 options for the number that goes atop them. I don't know, maybe they're like 1s or something, fine. But think about this case. I'm going to count it again when from my 4 dice, the 2 that I choose are blue and purple, right? Because I'm giving 6 options there after I choose blue and purple. One of those options is having a 1 on top of both of them. And then from the remaining 2 dice, red and green in this case, I got 5 options. This combination that you see in front of you gets double counted in this event space. And there's nothing special about this combination that'll happen for any 2 pair combination if you count them this way. So you got to divide by 2. Now I think this thing will work out. Let's see, 4 choose 2 is 6. 2 choose 2 is 1, so I don't even need to write it. This 6 divided by this 2 is 3. So I get 6 times 5 times 3 as the cardinality of the event space, the number of ways I can have 2 pair of matching dice. I can just kind of cheat and tack that on to my numerator here, pretending that I knew all along that there were 4 cases, not 3 cases to consider. Conveniently, this 4th case is also a multiple of 6, so I can still do the trick going down here where I factor out a 6 from each of these terms and cancel it with the 6 here. What I'd be left with is 5 times 3, in other words 15. So my numerator wouldn't be 141, It would be 141 plus 15. It would be, what, 156 divided by 6 to the third power? And hopefully that'll reduce and give me 13 over 18. I think it will, because 156 is divisible by 6, because it's divisible by 2 because it's even, and it's divisible by 3 because the sum of 1, 5, and 6 is 12, and 12 is divisible by 3. So let's see, what's 156 divided by 6? Well, 120 divided by 6 is 20, but then I'd still have 36 left over to get up to this 156, so I'd get 6 more 6s. So I got 26s and 6 more 6s. I got 26 6s. So 156 is 26 times 6. I take the 6 and cancel it with one of these 6s. I'm left with 6 squared in the denominator. In other words, 36. 26 over 36 reduces to 13/18. And would you look at that? After all that work and a mistake that you didn't even have to watch, I get the same answer that I got up here. Moral of the story, it's a hell of a lot easier to consider the complement than to try to consider all 4 of these different cases. You can do it this way, and it's not a horrible idea to understand this way, because a different problem on your test could easily ask you what's the probability that you get exactly 2 pair of matching dice, or exactly 3 with the same number up top or something. But I think a far more common question involves this "at least" phrase, and the test makers are hoping that you consider the complement and get the answer a lot more directly.